Welcome to today's presentation and thank you for tuning in. My name is Moritz Fischer. I am working as sales engineer at HAMAMATSU Photonics with a focus on analytical applications. Within this webinar, I will discuss some currently hot applications which implement near-infrared sensing. Our indium gallium arsenide, or short InGaAs, based detectors will help you implement those. What can you expect within the following 20 minutes? First, I will shortly introduce HAMAMATSU as a global player in the photonic industry. I will then discuss indium gallium arsenide as a photonic detector material. And even though there are some challenges, there are a lot of benefits in using InGaAs. So the presentation will be completed with a look into some implementations, ranging from basic sorting and quality applications to hyperspectral imaging in the end. First of all, why is HAMAMATSU discussing InGaAs featured infrared applications? Thanks to our long history and our strong network, we have provided many different industries and applications with high-quality components, and we want to share some insights with you. We take large pride in being a one-stop shop in the optic and photonic industry, and we are closely cooperating with a large number of OEMs who create photonic and optical devices and systems themselves. HAMAMATSU was founded almost 70 years ago, and we have grown our technology ever since. In my humble opinion, there are two aspects which make HAMAMATSU unique. First, we are present and in direct contact with our customers all over the world. Second, we put a tremendous amount of effort into research and development. This means we spend approximately 10% of our profits back into research and development work. And as customers, you can benefit greatly. We do not only have a wide lineup of standard components, but we are also always open for discussions of a product with customized specification. This means that in the meantime, we have officially registered more than 15,000 products, and those are, for example, lasers, light-emitting diodes, xenon lamps, deuterium lamps, and on the sensing side, photodiodes, linear image sensors, camera sensors, and the like. It even extends to X-ray products. Within this lineup, we see that there is one big trending product line, and that is sensors based on indium gallium arsenide. So its share is steadily growing in various analytical measurement problems, and that is reason enough to have a look on why this material is so important and popular. Just like silicon-based photosensors, which cover the visible part of the spectrum, InGaAs sensors can be used in a very similar way. But the major difference between those two is the spectral range which is covered. So let's have a look at the whole spectrum. For the X-ray and the UVC region, mainly back-thin silicon as a direct detector or silicon in combination with a scintillator are used. Then for the near UV, approximately 200 nanometers up to about 1000 nanometers, regular silicon is the material of choice. That is because it is cheap, it is mature, so it is an excellent basic material. However, silicon has a cutoff of slightly over 1000 nanometers. And that is the place where InGaAs as a material kicks in. InGaAs itself, in its standard form, has a sensitivity in the range of 900 to 1700 nanometers, but also above that, in the range up to 2500 nanometers, InGaAs can be used because there is a material composition which is called extended indium gallium arsenide. So nowadays, InGaAs is kind of a designer material which has several possible cutoff wavelengths. You can have, for instance, a look on a spectrum on the different sensitivity curves that we provide as a manufacturer. And thereby, it is possible that you can select a sensor which is the perfect match to your measurement task. By the way, above those 2500 nanometers, lead-based or mercury-cadmium telluride-based sensors are not the only options anymore. As an alternative, which is environmentally much more friendly, we are currently working hard on indium arsenide antimonide as a detector material which is capable of detecting light up to 10 micrometers. This could be as mature as InGaAs and silicon in the future, but it is a work in progress, so it is a whole other story. let's get back to indium gallium arsenide. For the imaging applications we are discussing today, one-dimensional and two-dimensional sensors are mostly relevant. So let's have a look at the general sensor structure that we are employing in those. Basically, an InGaAs sensor is a combination of an InGaAs photodiode array with several hundreds of pixels together with a CMOS readout circuit. That means the near-infrared light itself is detected by an InGaAs photodiode array, and the whole logic components are on a silicon-based CMOS chip. This comprises a timing generator, a shift register, the necessary hold circuits, and in some cases also a partial readout function. But the workhorse itself is the indium gallium arsenide based photodiode array chip. And in fact, it is not easy to design a powerful InGaAs chip which has sufficient performance for today's imaging tasks. So, because it is a compound material, there are several challenges InGaAs as detector material needed to overcome in the past. And generally, there are some parameters one needs to be able to handle well. Those are, for instance, the cutoff wavelength needs to be precisely controlled, but we will have an in-depth look into that later on. Further on, we need to have a sufficient resolution in order to capture meaningful images in spectra. Then we need to make sure that we have high enough speed for high throughput and high repetition rate in the application. And lastly, signal quality is very important. So the sensitivity needs to be high for low light conditions and small signals. And probably the most difficult part is to have an InGaAs material which has low noise and low dark current. The reason for that is mainly that due to the larger cutoff wavelength in comparison to silicon, there is a larger probability for thermally activated dark current, which you would measure as a noise in the end. But luckily at Hamamatsu we have a very long experience in manufacturing and developing compound materials such as InGaAs. We are a market leader in InGaAs technology with extended cutoff wavelengths, and therefore our sensors combine multiple features. Those are mainly a low noise, a high pixel uniformity, and we also have a focus on a variability in design. That means we have different package styles, different cooling options, and all of this will help you in the end to find a sensor solution that really fits your measurement task, but you will see that also later on. But before we have a glance at concrete sensor options, let's peek first into some integration possibilities. For this, I will shortly explain 3 distinct hyperspectral imaging configurations, because those combine spectral and spatial image capturing, and therefore they are somewhat representative. Hyperspectral imaging, in a nutshell, is basically the goal to obtain a two-dimensional image where each pixel contains finely resolved spectral information. So with this technique, you can quickly analyze the structure of a sample at each point of the sample. And the most basic method for this is the so-called point scan method. So for this detection method, it is best for you to choose a one-dimensional sensor. You will have the widest variety in our lineup of InGaAs sensors if you have a look at the one-dimensional type. There are various cutoff wavelengths between 1.7 and 2.5 microns. As you can see in the chart, there are many different interesting sensors which have different cutoffs, so you can freely choose based on your measurement task. For us at Hamamatsu, it is furthermore important to design our sensors such that they have a high signal quality. That means they are supposed to have a low dark current and a high signal sensitivity. That means our sensors mainly excel because they have a low share of defect pixels, and especially for one-dimensional sensors, there's a broad variety in terms of packaging. You can choose, for example, Peltier-cooled packages. There are sensors with flat cable packages for low-cost applications, and there are ceramic packages, and so on and so forth. However, if we pick a two-dimensional instead of a one-dimensional detector, one can greatly increase the speed of hyperspectral imaging. In the option B, you can see the so-called line scan or push broom method. Again, in this case, we need to map two spatial and one spectral dimension. In this case, the sample is scanned line by line by line, synchronous with a sensor which is moved in relation to the sample. So this is the first spatial component, while the sensor covers the second spatial component. And then, lastly, we gain a spectral component if we map the spectral resolution with a polychrometer on the second dimension of the sensor. So a polychrometer will split up the wavelength at each horizontal point. At the option C, this is the so-called plane scan method, and it is actually kind of ordinary in compared to the previous two types. For this, you take a two-dimensional sensor and the whole sample is taken in one single shot. This means the spectral information has to be gained with filters. So, for example, filter wheels are used for this sake. For completeness, there are further options to combine spectral and spatial capturing in order to achieve hyperspectral imaging, but this will not be part of this webinar here. We will now have a look at the sensors which are suitable for the two latter approaches. So, as already said, we need two-dimensional InGaAs sensors. And again, there is a wide variety of spectral ranges you can pick in order for you to match your measurement task. Again, there is the option to go up to 2500 nanometers, also with two-dimensional sensors. Our sensors can measure up to 507 frames per second, so that the high speed of your application can be readily matched. Furthermore, we also offer types which have a region of interest mode. So with those, you can increase the frames per second even more, or you can gain an extra degree of flexibility if not always the whole image needs to be captured. There are various packaging options. For instance, there are thermoelectrically cooled types. And what I think is interesting is also the transistor outline package, which is, for example, useful in compact airborne and drone applications. Think, for example, about aerial scanning of landscapes for agricultural interests and the like. And also, as a starter kit for this topic, we have a module solution which has the format of a camera and offers all of the readout mechanics needed. This will have further on a C-mount adapter, and it is simply coupled to a computer via USB connection. Lastly, again, very important for us is that our sensors have a focus on image quality. That means we want to have a very low share of defect pixels, because elsewise, with a high amount of defect pixels, this would be very detrimental for the overall image and spectral quality that you would obtain in the end. And so those kind of measurements would be less meaningful. This is exactly where our well-engineered production quality of InGaAs material kicks in. At Hamamatsu, we have a long-lasting history in the production of compound semiconductors, including InGaAs. And of course, there has been plenty of progress in the production process ever since. Thereby, our handling and the signal quality of our sensors have been largely improved compared to the past generations of sensors. This is especially important if you want to use extended cutoff wavelengths. Reason for that is that the indium gallium arsenide wafer is formed on a substrate of indium phosphide. For a sensor, it is important that the geometrical structure of the substrate and the wafer material is matched. So they need to have the same or similar lattice constant. This is a task for the manufacturer of the wafer. So sensors, dependent on their concentration of defect pixels will be sorted out, especially if the amount of defect pixels in the middle is too high. Thereby, you always receive a two-dimensional sensor with the optimum image quality. But let's get back to the product range on the market. For those of you who are focused more on the application side, or those who have no manpower for developing sensor peripherals, there is also the option to purchase fully equipped InGaAs cameras in our lineup. So there are not only 1D line scan cameras, but also 2D cameras either in QVGA or in VGA resolution. Those can not only be used for hyperspectral imaging, but also for general sorting applications and quality inspection tasks. Furthermore, you can freely choose the interface based on GigE, Camera Link, and USB. In comparison to our two-dimensional sensors on a component level, our cameras have further image processing functionalities on board. Those are, for example, background subtraction, shading correction, calibration of gain and offset, and so on. And also, we supply the drivers for easy integration. And again, just like with our components, for the cameras we also have a focus on excellent image quality. That means that low noise, high stability, and Peltier cooling is always on board with those cameras. So now you have seen that there is a wide range of different products on the market, and you can freely select the integration level that fits your need. You can choose different cutoff wavelengths, pixel formats, and so on. But I think it is very important to also show some image examples of what you can achieve with InGaAs sensors for imaging applications. That means at first I want to show two general sorting applications, and later on we will also have a look into hyperspectral imaging. We have shown an image from food quality inspection on a conveyor belt. The idea in this kind of application is always that water has strong absorption bands in the near infrared, either at 1.45 microns or at 1.9 microns are the prominent bands. The goal is to make visible where water gathers inside fruit and vegetables, because bruised spots cause an enrichment of water concentration at these locations. You can see these in the image with the tomatoes, and this idea helps us in the inspection of harvested goods. So you can, for example, sort the harvest into different categories, such as scrap or different quality classes. In the other schematic sketch, you can see a comparison of what you can achieve with a silicon-based sensor for the visible and an InGaAs-based camera for the near-infrared part of the spectrum. You can see that the silicon-based CMOS camera is useful for color sorting, but you can see no information about potential bruises. For this kind of information, the InGaAs camera will be needed in order to pick out different quality classes. In a similar manner, the InGaAs image sensor technology can help greatly to determine the water content in other industrial fields. For example, in the pharma industry, it is important to know the amount of water content or even the concentration of the active pharmaceutical ingredient, the API. That is because the water content will influence the absorption of the active substance by the body, and it will also affect the shelf life of a drug. In classical quality inspection, you would perform manual labor in a chemical lab. So this is slow and not really reliable under certain circumstances. In the imaging examples shown here now, you can see a comparison again of a visible sensor camera and an InGaAs sensor camera. In this case, you can even see that there is no real valuable information from the visible imaging. But if you have a look on the InGaAs image, you can clearly see a difference in terms of water content. As you can see, the right pill is dark, and that is because of the enriched water content. the water inside of the pill will effectively absorb the near-infrared light, and hence you can distinguish between water-rich and water-poor tablets. So with those kind of cameras, you can measure the quality with high speed and high accuracy. So these two examples of standard imaging applications are kind of straightforward. What I think is really fascinating and what has a lot of potential is hyperspectral imaging. For this, I want to have a closer look at plastic recycling. As you can see in the charts, global plastic production is steadily increasing. In the diagram by the OECD, you can see how wealth and development of countries has led to an increase of plastic production on a global scale. And this usage of plastic grows and grows and grows. This has been taking place since the 50s. So in return, recycling needs to hold up with that trend. And it has a much better energy balance if you recycle plastic rather than producing new plastic materials. You can see on the other chart, there is luckily a trend into the right direction. So recycling rate is growing and growing. And in Europe, we have, for example, approximately 30% by now. But there are two technological implications. Not only do you have to increase the speed at which recycling is performed, you also need to have excellent accuracy in recycling. Reason is that there are many different types of plastics in circulation which have similar signatures. But as you will see, a promising solution for this is near-infrared hyperspectral imaging. If we have a closer look at the problem itself, let's have a look at the typical recycling configuration. The plastics from the trash are transported on a conveyor belt, and those then must be sorted by the different plastic type. So the goal is to differentiate different materials at a high speed. And imaging in the visible part of the spectrum is not really helpful, especially transparent plastics. I'm pretty sure you can relate that there is a lot of transparent packaging material in circulation if you think about grocery shopping, for instance. And colored plastics, in turn, can even disguise the type of raw material if you use visible imaging. So such a kind of plastic sorting application is particularly suitable for hyperspectral imaging because we can make excellent use of the push broom technique already presented. The hyperspectral camera will be placed above the conveyor belt and the plastic will be pushed below in relation to the camera. And so at each imaging step, the horizontal component and the spectral component will be measured by the two-dimensional camera. If we have a look now at the spectral signatures of different plastic materials, you will see that especially in the range of extended InGaAs above 1700 nanometers, those popular plastic materials will have especially distinct characteristics. So have a look at the chart and you will see that popular materials as PVC, acrylic plastics, PET, polystyrene, all of those have distinct features in the indium-gallium arsenide range. So if we use appropriate chemometrical methods and algorithms, we can distinguish those spectral compositions, and this kind of information will help us discriminate and sort the materials. So to sum this up, if we take into account the spectral knowledge that we have, we could even say that transparent plastics become colorful in the near-infrared. And there is plenty of more things to discover out there, and more suitable applications will emerge over time. And we do not only see a trend towards general near-infrared imaging, but also to these kinds of hyperspectral imaging implementations. In terms of content, I am finished at this point, and I hope very much that this webinar gave you a learning about InGaAs, a sensor material, and also about some potential near-infrared imaging applications. I think there is a great potential out there, And if you have any kind of questions or requests, please do not hesitate to get in touch. You can always get in touch with Hamamatsu globally, but of course you can also contact me or my colleague, Mr. Wöhnl. And furthermore, if you think that this has been a great and informative format, you should also check out the other contents of our webinar series. They will deal, for instance, with optical water analysis or the measurement of fluorescence signals. Thank you very much for tuning in, and take care.